and we'll try to be in time. The first presentation of Mr. Reza Boudares was cancelled. He cannot reach the workshop, so we will begin by Mr. Kochanek.
Oui.
Krzysztof.
Yeah. Good afternoon, everybody. My name is Krzysztof Kochanek. I'm representative of Institute of Geophysics, Polish Academy of Sciences. And today I would like to present some results of our work on inundation risk for embanked rivers. This is a consequence of a work which we did together with Professor Strupczewski, Dr. Markiewicz, and Dr. Bogdanowicz, who unfortunately is not here today. So I skipped this slide because as far as I know, I have only a quarter, right? So you will see what I'm talking about. Embankment of the rivers is the most popular way of flood protection in Poland. I guess not only in Poland, but in most of the countries of the world. But in Poland, the dikes are usually 100 years old and in very bad shape. Repairing them costs a lot of money. Of course, we have crisis. There is not so much money to repair the dikes now. And what's more, they give just the illusion of safety behind the dikes give just the illusion of safety from the floods. As we see at this picture, the illusion can be really strong. We can talk about two probabilities of flood in embankment rivers. The first probability is the overflow of the levee's crest, which is quite obvious, but at least in Poland it's a very rare case, almost not happening. We didn't have records of such events in Polish rivers. The second one is that the levee breaks because of the impact of the high water above certain alarm level, and this is quite often in Poland. What's more, the levee breach occurs when the highest point of a flow already is gone. So people feel relaxed, give sigh of relief, but it's not true. They should be alert all the time until the water gets back to its old banks. So the overall probability of flood in the embanked rivers can be depicted as the sum of P1 and P2 probabilities. And in these pictures, at the bottom we have P1 when the water flows over the levee's crest, and on the right-hand side we have when the levees breach. Here we have a diagram, an illustration which helps me to introduce some nomenclature. QAQ, it's quite unfortunate name for it, but QAQ stands for alarm flow, above which, if water stays for a certain time, it may soak through the dike and cause the flood. And QB stands for the flow above which the water flows over the crest. So as you see, it's connected with risk of overflow P1. QB is connected with P1, and QAQ, sometimes it's later called also AQ. It's risk of a levee breach because of a long exposure of a dike to the high water. And a few formulae. P1, it's quite obvious. It's just the probability that the flow is higher than the highest point of the crest. This is quite easy. We know it from the primary school. Probably some of you know it even from kindergarten. So I'm not going to talk about this now. What is more interesting is the P2. P2 of flat, FL stands for flat, where the flow is between the alarm flow, QAQ, and the top of the crest. And this is also quite obvious. But if we see at the lower line of this integrate, we can see a little letter D, which stands for duration of the water stay above the threshold, alarm threshold, and D, which is duration, will be the hero of our story today. So how it started? We know classical, traditional flat frequency analysis is about finding the probability of annual, seasonal flow above certain level. So we tried to introduce another parameter, which we called duration. But if you look a bit closer, it is also a kind of parameter which defines the shape of the hydrograph. So as we can see at this diagram below, the D is additional parameter which helps us to define the flat, in fact, the risk of the flat. And historically, the first model which involved duration as a parameter in modeling was QDF. D is small letter because it's about this later. And this was the extension of standard flat frequency analysis, so the flat duration frequency modeling, where we can define a number of days, let's say 5 days, and try to find at what level these 5 days fit into the hydrograph. It's like in this diagram. And the natural consequence of QDF modeling was the DQF modeling. Sorry for this equilibristics here, but it is defined in these 2 points that Q is a random variable, therefore is written in capital letter. Duration is a constant value, therefore is written in small letter, and frequency is also a random variable, therefore is written in a capital letter. Whereas in DQF, which is the approach which I'm going to talk about now, is a dual to the previous approach. So we have flow, a fixed value of a threshold. This is this alarm flow which was mentioned before. Duration is a maximum uninterrupted duration of river flows for a given threshold AQ, and it is random variable, therefore it is in capital letter, and frequency is also a random variable and it's capital letter. So how it works in practice. Here we have a fragment of hydrograph for 1962. It's actually, as far as I see, it's 4 months, and we can see 2 big flats here. 2 big, not flats, but flows here. One is around 3,000 cubic meter per second, and the second one is half this value. And normally, in classical flat frequency analysis, we would take the bigger one, right? But now we are concentrating on the duration, and however, the second peak is higher, we take the lower one because it lasts longer. So the water above 700 cubic meter, which is marked by this green line over here, stays longer. So it has more time to soak through the dike and to destroy it. As a result of such an analysis of hydrograph, we end up with a series of the durations of uninterrupted durations for each year, the longest uninterrupted durations for each year. As you can see in this diagram below, these red bars are not occurring every year. So it means that in that year there was no flow which exceeded the alarm threshold. So we noted that it is 0. So as you see, we have, for instance, in 51 we had 2 days of stay above the threshold letter, 52 none, 53 no, none, 54 1 day, and so on and so forth. Yes, the question arises. We are used to modeling of parameters which are continuous, but as you can feel it, the duration is not continuous. It's discrete, because you can count it. It's 1 day, 2 days, 3 days, 1 second, 2 seconds, and so on. But the model itself doesn't have to be continuous. In fact, it consists of 2 parts. The discrete part, which is here, we can see beta times delta from D. Delta is Dirac's delta. So this part is responsible for the cases where there is no flow above the certain threshold level. And the second one is a continuous part where we can model the frequency of occurring of the duration above of water stay above the certain threshold level. Sorry. So as you see at the result, we have a mixed PDF, discrete, continuous. The good news is, however, when we use the maximum likelihood approach to estimate parameters of such a model, we could separate the continuous from the discrete part. So at first we can very easily estimate the value of beta. The beta is a parameter which switches on and off between discrete and continuous part. So as you see, it is very easy to estimate such a value. And one is a number of years where the flow above threshold doesn't appear, and then N1 plus N2 is the entire length of the series. However, there is another way of estimation of the beta parameter, which is a bit more detailed, but a bit more time-consuming and ambiguous. It is very similar, actually. It is classical flat frequency analysis when we fit a distribution into the data and try to find a quantile for this, or rather probability in this case for a certain quantile. And as you see, for our case study, Szczucin, we have a small difference between these two estimators. Well, let's say technically there is none. So the first estimator, which you saw previously, is good enough for this case. We will see later that it doesn't have to be like this all the time. And how about the continuous part? The continuous part, we saw that the best probability distribution functions are kind of exponential alike, which are, this kind of distributions, which, first of all, this is exponential, generalized exponential. About generalized exponential, my colleague Ivona will say a bit more in half an hour, so be patient, please. And the gamma, variable, and so on. For our case study, we use generalized exponential because it's new. It has never been used so far, so why not try? And alpha is the scale parameter in this, and beta is the shape parameter. What is important? We don't deal with x, but we deal with d. You see that the variable of this distribution is not x, it's not flow, but it is d, which is duration. This is important to remember. And of course, Taha said that if there is a sign of non-stationarity, we should try at least to use to employ non-stationarity in our models. As you can see, we did it by adding another parameter, which is time covariate, which is time both to discrete and the continuous part of our model. So maybe I just skip the case study. If somebody is interesting, I can show it during the break, but I don't think so. Let's get to the conclusion. DQF modeling is the consequence of KDUF approach developed by Mr. Javel and extended by Dr. Bogdanowicz. The DQF consists of three terms, which is continuous and determined. As you see here, both beta and f with a circle are maybe non-stationary and may depend on time. The maximum likelihood message is the best method of estimation of beta and g parameters. The beta parameter can be also estimated by means of annual peak flows. And in non-stationary case, the function of beta is best described by the logistic function. And for the f with dot, for non-stationary and stationary case, are best modeled by exponential-like distributions. I didn't show the case study, but I will show the conclusion drawn from this case study. The calculation for the Szczucin at the Vistula River confirmed the strong dependence of beta on the threshold, diminishing the importance of the second term, which is the continuous term. And the general rule is that the higher value of threshold, the thinner tail of the DQF function one gets, which is quite obvious because the longer the water stays above the threshold, later it's less probable that it stays so long. And in non-stationary case, the time variability in the duration in the f in the continuous term is negligible because the shape of the model doesn't change. The only trend can influence the form of the beta parameter. And this is important complexion to the traditional flat frequency, and is especially useful in Polish specific condition where the flat protection infrastructure is dated and often does not survive confrontation with long impact of high waters. Thank you very much.
There is some confusion about what duration is and whether it is a random variable or constant. And you very well explained that in one case it is a constant and in the other case it is a random variable. But my comment is that we could use two different terms. And in the first case that it is a constant, we should not call it a duration. We should call it time scale. Okay. Or time window. Of course, this is a general problem. For instance, we use the term IDF curves, intensity, duration, frequency. Again, this is not duration. This is time scale which we describe the variable. And again, perhaps the frequency is not the correct term, it's a return period. And frequency is the opposite, the inverse, but we use it as if it were period. We use the term frequency. Just my question is, this was my comment. My question is, I didn't understand exactly what the time t is and which induces non-stationarity. Could you explain?
Yes, yeah.
Yeah.
Maybe I just go to, which is beta, also can rely on time, which is the...
What time? Time of the year?
Variability of time. No. Over the certain years, over the length of the time series which we have for our modeling. For instance, at the very beginning, the occurrence of floods above a certain threshold level may be more often than at the end.
But do we know this deterministically? Do we know the variability deterministically?
Well, I think
we describe in statistical terms. So we can, again, I think we cannot call it non-stationarity. It's a conditional probability. Conditional probability is different from non-stationary.
Yeah, but we treat it as a non-stationarity. Again, we introduce some, for instance, linear trends to beta variable. You can estimate beta variable on
in the past. What about the future?
Well, I didn't think about the future. I live in the past.
Okay, but you predict the future.
Going back, that beta is just an alarm flow. Yes? Beta is just AQ, alarm flow. So beta T is just the changing of alarm flow in the time. So it comes, for instance, from the non-stationarity frequency analysis. You take these values, alarm flow, and you find how it's changed in time. Okay? So it means that it is just we put non-stationarity only in this case in beta. We didn't put to this second term. Perhaps it is possible, but the data is too little data to take such thing. Okay?
Yeah.
Thank you.
Maybe beta.
I have a different opinion.
Okay. But you don't agree with it? Yes?
Maybe beta is related to the age of the day.
No, beta, because beta is because you have a damage. It is linked to a damage of the dike, maybe so. But we may discuss further. Now it's time for Mr. Nugent. Ronald, thank you. Thank you.